So you do not want acetylcholine to be broken down too soon, but you don't want it to sit around too much. Okay? So there's a delicate balance to how much acetylcholine gets released, how much binds to the receptor, and how much gets broken down. Everybody agree? And those three factors are what's going to determine whether I go from resting membrane potential, which I'll no longer write again, right? I'll always write it as RMP. Okay? RMP, resting membrane potential, versus the threshold potential, versus your max potential. And this is all within one single muscle cell twitching, guys. One single muscle cell twitching. Okay? And you have to have this electrical event to be able to get the mechanical event, remember. So the electrical event, this allows for what? An increase in sodium, which takes me to threshold. But once I get to threshold, then I'm activating what? Oh, I'm activating voltage-gated channels. And my shorthand for channel is a C with a line through it. And that's going to be a sodium channel. And that's going to be fast sodium channel, right? Fast to open, fast to close. So fast sodium channel is a voltage gated channel. Well, that's not the only one I trigger. Thing is that the other one that I trigger is slower to open because it's got two doors versus sodium has only one door. So I go all the way up and then I come all the way down. And on this side, then I've triggered open the voltage-gated potassium channels that are slow potassium channels. Okay, so the voltage-gated sodium channels that are fast sodium channels. They're fast to open, fast to close. Here, the voltage-gated potassium channels are slow to open, slow to close. There's more than one gate that has to open for the potassium to leave. Unlike the sodium, there's only one gate there's only one door to open and the sodium comes in. For the potassium, there's two doors that have to open for the potassium to leave. So that's why it takes longer. And again, once you open the door, you have to wait for the door to reset. Okay? It's not like a garage door where you can press the button once and then the garage door goes up and it stays open. No. The cycle is, and this is the rule, when you open it, you have to shut it before it can open again. Okay? That's the rule. On the membrane, that's the rule. So any one of these that we're talking about, if it's open, you have to wait for it to open completely, for it to then shut completely, for it to then be able to open again. Any questions so far? Any questions, guys? All right. So my main concern then, once I get here and I want to get back down to rest, then I have to contend with two other ones, which is the potassium weak channel that's always really leaking, and the 3 sodium out for 2 potassium in. ATPase pump because it's spending large amounts of energy pushing things up and down. And then what happens is we get this overshoot, and that's called hyperpolarization. Versus I was at positive and coming back down to my threshold. That's called repolarization. And then this is called depolarization. Now remember, the whole idea is this has to happen everywhere on the membrane of the muscle cell for you to have this electrical event. So this has to travel. This wave of depolarization has to travel across the membrane, the sarcolemma of the muscle, down the T-tubule, and stimulate it. Okay? So this wave of depolarization, or depolarizing wave, must travel across the sarcolemma through T tubules to reach dihydropyridine ryanodine receptors associated with SR, which is calcium storage site. Okay? So that depolarizing wave must travel across the sarcolemma, down through T tubules, to reach the dihydropyridine ryanodine receptors associated with the SR that stores calcium. So those dihydropyridine ryanodine receptors, they're that plug in the sink. You pull the plug of the sink, and what? The sink empties, right? So the sarcoplasmic reticulum has calcium in it that empties into the cytoplasm of the cell. Now you got excess calcium, you got lots of calcium on board. I got increase in calcium concentration in the cytoplasm of muscle. They call that the sarcoplasm. Did everybody hear me? Because it's not a single cell, it's what? It's multiple fused myoblasts that became that functional muscle cell, right? So we got to give it special names for all the structures that are in there. So the cytoplasm, we don't just call it cytoplasm, we call it sarcoplasm. Did everybody hear me? We don't call it cytoplasm, we call it sarcoplasm. Plasma. All right? So instead of cytoplasm, right, they call it sarcoplasm. Now that increased calcium concentration in sarcoplasm, what that'll do is it will remove troponin / tropomyosin. Okay, it removes troponin, tropomyosin from actin. So now myosin and actin can interact via cross-bridge cycling, ATP dependent. That means I need glucose, I need oxygen. Ready to follow? Now, the amount of glucose and the amount of oxygen will depend on whether you're talking about white fibers or red fibers. Are you talking about white muscle fibers that can sustain longer muscle contractions versus the red muscle fibers that can sustain muscle contractions only for short periods of time? That's the difference between people who can run very, very fast or very short distances versus people who can run very long distances because they have more white muscle fiber on them that can sustain and sustain and sustain. Okay? There's what they call slow twitch versus fast twitch muscle fibers, and they're also in the textbook. Okay? Separately, guys, so here's the whole thing. Myosin and actin, there has to be overlap. Okay? So let me see. Let me get two people up here. Two volunteers. Come on. Two volunteers. Careful with the cable. All right, so I want you to stand right over there. I want you to stand right over here. And just stretch your arms out for me. So this arm is myosin, actin. This arm is actin. Now you can only see me because I'm myosin, I'm the M line. Each one of them are Z lines. Actin, actin, M line, myosin, myosin. Everybody follow? Everybody see that I must have some overlap between the actin and myosin so that when calcium is present, myosin can reach up, grab, and pull the actins. And what that does is it brings the Z line towards the M line and the Z line towards the M line. Understand that? Well, the distance between Z line and Z line is referred to as a sarcomere length. So when a muscle contracts, you're shortening the sarcomere length. I'm not cutting my arms off. We're not cutting their arms off. but we are shortening the distance between Z line and Z line. And that's the sarcomere length, guys. You understand that?
And you said that's making your muscle contract.
That's what makes the muscle contract. Now watch. So at rest, we tend to be a little bit more overlapped. So we're like that. Now what happens? I'm a professional athlete, and I'm going to go play basketball. What am I going to do before I go play ball?
Stretch.
I'm going to stretch. Everybody ready? When I go to stretch the muscle, I do this. I don't overstretch, so that I have zero overlap. I get stretched out where I have just enough overlap where I can grab and pull the Z line further from its original position. Do you see that? That allows for more forceful contraction. Does that make sense, guys? Does that make sense?
Yes.
Yes or no?
Yes.
Yeah? So now watch. If I go too far now, step a little further that way. If I go too far, guys, can I have interaction?
No.
So does everybody see? You can't overstretch the muscle. Because if you overstretch the muscle, then the muscle what?
Tears.
It tears. The myosin and actin can't interact with each other. And if they can't interact, then the muscle can't contract. You gotta let it repair itself. So what does it do the next time around? It'll take and start repairing the M line and the myosin. It'll put more myosin, more M line. It'll put more Z lines, more actin. And each time it'll go and repair itself. If you give it time to repair, and if you consume enough protein for the purpose of repairing the muscle. That's when you start consuming more protein. You don't start consuming more protein the first day you show up to the gym to work out. You gotta wait at least like 4 weeks before then, right? Unless you're really, really working out really hard, right? So let's say at the end of 2 weeks. You're going in there, you're serious, man. You've been in there, you've been pushing yourself, and you're in pain the first week. You work through the pain, the lactic acid, you're really pushing yourself. Then maybe, 2.5 weeks, maybe you could start taking a little bit of extra protein supplement. People are buying protein supplements before they even go to the gym, for Christ's sake. They're taking the protein supplements to replace the meal. That's not what it's for. What does protein supplement mean, guys? Supplement. It means it's to be added to your meal, not to be taken as a meal, as a replacement meal. And then sure enough, I'll have people come up to me who are doing just that. They go to the gym, they buy a supplement meal, and then they wonder why their urine smells all funky and why they're starting to have problems with their kidneys. And I'm like, stop using the supplement. So guys, this whole idea, we have to have overlap. We can't have no overlap. We have to have some overlap. At rest, we have more overlap. When we stretch, we have less overlap, which means we can create a stronger contraction. That's the idea. Why you want to stretch before you work out. Don't go do the weekend warrior thing where you don't stretch or anything, then you just go and perform. That's how you hurt yourself. Guaranteed injury. Guaranteed injury. All right? Thank you, guys. No problem. All right? Any questions? So that overlap is key. Always. Actin and myosin must overlap. But they can't always... But wait. So even at rest, guys, we have a certain amount of tension on our muscles. Did everybody hear me? And separate of that, the spinal cord and brain are constantly monitoring the stretch on your muscle. I can prove it to you. I'll take any one of you and I'll bring in my reflex hammer and I'll start hitting spots. And I'll hit the spot and what'll happen? Your arm will flail. Your leg will flail. Right? I can hit this one and you'll kick, right? Those are reflexes. I'm convincing your body that your muscle's being overstretched. And then it's sending that information back to the spinal cord. Spinal cord is then sending information back to the muscle to tell the muscle to contract. Don't go too far away. If you go too far away, then they can't interact. Myosin and actin. Does that make sense, guys? So our brain and spinal cord are constantly measuring the stretch on the muscle. And we do this by looking at the actual stretch on the muscle and the actual stretch on the tendon. Because if I stretch the tendon, I could be stretching the muscles. Everyone agree? And I could be stretching the muscle, right? So vice versa. The muscle could be stretched, the tendon could be stretched, so I got to measure both. So sure enough, I have devices by which to measure both. They call it the Golgi tendon reflex arc, right? And the muscle spindle reflex arc. So within the muscle, we have special muscle cells that are wrapped with sensory neurons that are sending that information back about the stretch on the overall muscle. Does this make sense, guys? Can't have too much stretch. If you have too much stretch, then actin and myosin can't interact. So it's okay if we're closer together, but it's not okay if we're too far from each other. Does everyone agree? And we're talking about actin and myosin overlapping. inside one single muscle cell. If you get a whole bunch of muscle cells that are in a fascicle, or the whole entire muscle gets stretched out of whack, man, you're not going to be able to use that muscle for a long time. Does everyone agree? You better hope you don't damage the muscle that bad. Hope that you don't damage the muscle that bad. Because the reality is, hey, what you got is what you got, right? You really can't make new muscle, right? There's some satellite muscle there, here, and there, but the idea that you're going to engineer it the same exact way as you did before, just like kind of connective tissue, it's not, the science isn't there yet. It's just science isn't there. Just like with nerves, we used to say you could repair nerves. Yeah, you can. You could repair peripheral nerves if the sheath is still there, if the myelinators are still there, if the cells that myelinate the axon are still there. All right? And if all the growth factors are there, depending on whether you're young or old, depending on diet, exercise, all these other things. So the science isn't there for us to be able to just say, oh, don't worry about it. You ruin that muscle, we'll just fix you up. Although, to be honest with you, muscle can fix a lot better than connective tissue can. Of course, liver can fix better than anything. Right? You lose half your liver and then your liver regenerates. Right? No, stomach. Yeah, last thing you want to do is start messing around with your stomach. Now, the lining of your stomach is constantly being replenished daily, just like your skin. Constantly, the cells are constantly being replaced, constantly, daily, like all the time, just being shed, constantly being shed, because they know that there's a harsh environment down there, harsh chemical environment, and all the stuff that we're getting exposed to. We're all shit eaters, so we got to constantly be shedding away, just to make sure that our organs don't get sick. So, but muscle's something special, and especially when you're talking about skeletal muscle. Now it's really cool is that they've done stuff where you lose a muscle because of a severed nerve, and they've been able to graft a separate nerve onto the muscle and get the muscle to work, which I thought was amazing. That was really, really, really cool. All right, this is in the military, in the army. So you get some of these guys, they get damaged to shrapnel, they get damaged to the nerves in their arms, and one of the muscles that he needed, which is his pec major, the nerve got severed. So everything else healed, and what they were able to do is they were able to take one of the smaller nerves that goes to the pec minor and connect it to the pec major, which there is, but they were able to graft more of it on there, so he was actually able to move his arm better because they were able to regraft a new nerve onto the muscle. So it's quite amazing how muscle can adapt to stimulation of neuron. But the key is to have that neuron there. If the neuron gets disrupted, then that muscle's going to be, it's a matter of time before that muscle dissipates. Now, you can get it, you see some of these people, like if you go and you look at severely depleted individuals, caloric-wise, right? People who, like concentration camps, you look at them, they're all skin and bones, yeah? Well, in that case, what happens? The body will consume, when need be, it will consume and metabolize muscle to try and prevent your glycogen stores in your liver from being, used up completely. And so you wind up little by little, as you go through long-term starvation, you'll wind up destroying muscle. And this is why you'll see these people, you'll see pictures of these people, they're all just skin and bone. Now, it's even more interesting is, the muscle doesn't quite, because the connections are still there and the muscle's still there, it's just an issue of diet. Sure enough, if you feed them, within 2 to 3 weeks, you feed them, and all of a sudden now they're gaining mass again, and they get back everything. So, they may have some, depending, again, if the nerve is damaged, right? They may have some issues. But if the nerve is not damaged, then they may have no issues at all. Even though they did lose a large amount of their muscle mass, they didn't lose the cells. You understand? They lost what was inside of the cells. As long as you have the cells and they're around, you can always re-architecture what's inside the cell. You understand? As long as you have it in your diet. So in those cases, people who are long-term starvation mode, you give them what? You load them up on a positive nitrogen diet, or positive amino acid diet. You load them up on more amino acids because that's what they need to be able to reestablish that muscle. And the muscle will do it fairly quickly as long as they're being fed the essential amino acids, 10 of them, or 11 of the essential amino acids that we need for proper muscle formation, for proper protein formation. Very important, very important. So this dihydropyridine rhinodine receptor, I'll never test you on it. But I mention it for a reason, and it's to drive home a message. Bill Cosby deserves to spend the rest of his life in prison. This guy's a serial rapist. The drug that he used on his victims targeted this dihydropyridine ryanodine receptor. And if I target this receptor, what happens? I don't get calcium release. Does everyone realize that? So if I give enough of this, I don't get calcium release. That means then what? I decouple the electrical event from the mechanical event. This is where women wake up. The women will wake up, but they can't move. All right? This guy's a serial rapist. He was doing this, even though the women probably would have slept with him without him having to administer the drug. And somebody taught him how to do this. And I guarantee you, it was a doctor, or I don't even want to go any further with it, but a sick individual nonetheless. Right? Because I watched all those videos, and every single one of them is a common theme, was that they woke up in the middle of it and they had no control over their muscles. So they're there neurally, they're there awake, kind of like dazed, right? But not capable of moving. Right? That to me is just, so that's kind of why I write it down, because I really want to strike home this idea that you need that calcium, guys, to have that troponin, tropomyosin be removed from actin for the actin and myosin to interact as long as ATP is present. And that means as long as you have a good oxygen supply. Of course, don't forget that skeletal muscle cells, and within muscle cells, it's not just about actin and myosin and troponin, right? Actin and myosin and troponin, tropomyosin. It's also about myoglobin and the enzymes necessary to produce glycogen, which is glucose storage. All right? And then also creatine phosphate for the first 60 seconds of exercise. So you don't have to wait for your mitochondria to make ATP. You don't have to wait for glucose to come from blood. You don't have to wait for oxygen to come from blood. The muscle's got everything it needs for the first 60 seconds of exercise. Do you understand? Beyond that first 60 seconds, it's not going to demand of the blood. It's going to demand of myoglobin to give oxygen. It's going to demand of glycogen to feed its mitochondria. You understand? And the blood supply. All right? So creatine, another one is, you'll hear it, people loading up on it now, I have no clue why. It's only for the first 60 seconds of exercise. That's it. Right? Like, why would you continue consuming excess amounts of this stuff? It's only going to use it for the first 60 seconds of exercise. It makes no sense. But sure enough, hey, it's a great product. It has results. Of course, they show you these guys that have been lifting their whole lives, right? They can consume anything and look that way, right? They could eat Twinkies, right, for the next 5. Well, maybe not Twinkies, right? Because if you eat Twinkies, then of course the little injections in the back, right? You know what will happen in 5-10 years. You just be all water, right? It's my friend. When I was in undergrad, he'd walk around, he was all built, right? Super built, always going to the gym every single day. And then now I see him and he's just like this big bag of water. He's just, because he was using the juice. So it's not real muscle when you use the juice. It's not. And then you ruin everything else. Because by taking the hormones, then your testicles shrink. And you stop producing the hormone that you need because you're taking plenty of it. Why do you need it? Make it for if you're taking it. So, all right. So any questions on this stuff, guys? This is general muscle. General muscle, how it works. Now, guys, skeletal muscle is voluntary. Has a special function. Has a special form. Has a special function. Cardiac muscle. Would you think it'd be the same? Skeletal muscle? No. Has a different function. Does everyone agree?
Yes.
So it should have a different form. Yeah. So sure enough, cardiac muscle, just to be thorough, cardiac muscle, guys, they're uninucleated. They're single-celled. They're branched. So those are the nuclei. The nuclei are peripherally located. Then they are highly striated. Similar to skeletal muscle cells. But they're involuntary, guys. They're involuntary. So they're highly branched, uninucleated, and the branchings. In these branchings, you find these huge proteins. They're called gap junctions. The gap junctions are so predominant that they actually refer to them as connexons and also as intercalated discs. Now, why would I want a big channel? Why would I want a big channels between these cells? Where would I find these cells? In the heart. Would I find these heart cells anywhere else than in the heart? No. Does everyone agree? No. So these heart cells, well, what's one unique thing about the heart?
It has its own electrical system.
Good. It has its own electrical system. Okay, good. What else? Does each one of my heart cells contract on its own?
No.
Yeah, that'd be called AFib or VFib. No, you don't want none of that. That's not good. You want all your atrial cells to contract. So we have 2 atria and 2 ventricles. We want both atria to contract and then relax, and then we want both ventricles to contract and then relax. Did everybody hear me? Did everybody just hear me? I want these structures that these cells make up to contract together at the same time. Do you everybody hear me? To do that, what one cell senses, what? They all have to sense too. Do you agree? That's why I got these big old channels in there called intercalated discs or gap junctions or connexons in there. You ever understand that? That's why they're there. They're there to ensure, hey, when I get the signal, both atria, you ready? Contract. Then, both ventricles, you ready? Contract. Can't work any other way. You ever understand that? Smooth muscle's the same way. The difference is smooth muscle is not highly striated. It's uninucleated. But when you look at smooth muscle is fusiform. Smooth muscle is fusiform. Called fusiform. And then what happens when it contracts? Depending on its arrangement, it'll kind of like shorten. Everybody see what it? The actin and myosin are there. You just can't see it. And there's not a well-developed sarcoplasmic reticulum. So if I don't have a well-designed sarcoplasmic reticulum, where the hell am I going to store my calcium, guys? In the cytoplasm. Does that make sense? If I store it in the cytoplasm, can I just have calcium floating around in the cytoplasm whenever? No, so I got to have some way of regulating it. Did everybody hear me? So sure enough, in the smooth muscle, calcium storage is not through SR, it's via calsequestrin. It's a calcium protein that can act like a sponge to calcium. Did everybody hear me? It's got multiple sites that it can... Come here, calcium. Come here. Come here, calcium. Since I don't have any place to store you, come here, calcium. Come here. You're in the cytoplasm. Come here. You need to come here. And at least stay here. Everybody hear me? Now, something else that makes cardiac and smooth muscle different from skeletal muscle is that myosin in skeletal muscle. Myosin. So in skeletal muscle, guys. Myosin in skeletal muscle. So skeletal muscle, myosin has 2 activities. One, it has 2 activities with ATP. Okay? The first is when you look at myosin, right? This is where actin wants to play. So actin wants to play right there. That's the head of myosin. Well, myosin has a separate site. That site is for the binding of ATP, adenosine triphosphate. But not only is it the site of the binding of ATP, it's also the site of the hydrolysis. So not only does it bind ATP, it also hydrolyzes ATP. And by hydrolyzing ATP, it makes it ADP, and one of the phosphates goes off. And by doing that, that energy gets transferred to the site where, so the actin binding site. Bless you. The actin binding site. So when I take the ADP, the ATP, and I find that third phosphate, and I take that energy between that third phosphate and the second phosphate, that energy, I can take it and I can give it to the myosin molecule. You got me? And by doing that, I can activate the head of myosin, which will grab up and contract. Did everybody see that? It'll grab up. My myosin will grab up to actin and then pull. Now, it's connected. For it to release, a new ATP molecule has to come in. Everybody hear me? So this guy has to leave now. Now actin is bound. So now we have our actin bound. So there's our actin bound. Well, then a new ATP molecule has to come in, and when that is there, then it signals the release. This is what we call cross-bridge cycling. Again, I wrote it down there. Make sure you go and look it up. It's in your textbook, and it's in the homework, assigned in the homework. All right? So that's something that myosin in skeletal muscle has the ability to do. Did everybody hear me? It has the ability to phosphorylate itself. Did everybody hear me? It has the ability to activate itself. Well, in cardiac and smooth muscle, myosin